So go after that, everyone. So for the next 1 hour, I will talk about this work joined with Ibrahim, which is joined in Zoom and then social media. Okay, so the outline for network will be 5 parts. So first, I will explain briefly what is MaxMin-Omega system, which is simply the generalization between max plus and min plus, and then next part I will talk about the problem formulation, which is simply the linear equations, but we have different system, and then we have 2 cases where we consider the property of the matrix, which is when the column of the matrix distinct or indistinct. And then for final part, I will mention some feature work that we find interesting. Okay, first, for those of you who are not familiar with Maxwell's algebra, so you can think of as extension or the modification of linear algebra, where we usually have real numbers, but here we have real number with minus infinity. And then we also modify the operations. The normal addition we change to be maximum, so A plus, usually we call A O plus. A or plus B means the maximum between A and B, while the O times simply A plus B. The dual of the max plus and min plus, simply we have minimum for the additions. And of course, this operation can be extended to matrix and vector in the natural way. So, for example, these matrices, when we multiply, simply take the first row and then the first row of the first matrix and the first column of the first matrix, and we multiply. So 1 plus 3, which is total is 4, because 1 times 3 in max plus is 4, and then we have 4 times minus 2 is 2, and then 2 times 2 is 4, and then we take the maximum, which is 4. And then we do the same for the rest. And if we choose the operation matrix multiplication in min plus, so we do the same, but we take the minimum. That's the idea of the multiplication from linear algebra to max plus and to min plus. Now, the interesting part of the modification, this is by Ibrahim axis. Instead of taking the maximum or the minimum, how about we take the something in between? Think of like fudging, when we are not only 0 and 1, but we have something in between. So, for example, in max plus we have the largest or the latest one, considering as the input, and then we take the largest one, and then for min plus, which is the smallest or the earliest. And then this is just the notation. So this one meaning the kind of like sigma in the algebra, we have a big O plus, meaning we have a set or multi-set with this S1 until Sn, and then here we have to take the maximum between this set, while this one is the minimum. Now we have the threshold omega, which determine the output of the set, meaning if we take omega for a value that is really small, we take the smallest one, which is represent the min plus. If we take the omega equal to 1, which is the largest one, and for example, if we take omega equal to a half, which is the middle element, after we order the set in this the element on the set. If we define this one, the generation of these 2 operations, we have this what is it, subscript omega, which is simply when the member of S has n, and then when we consider P as this scalar, then this notation simply the P smallest element on S. So for example, okay, this one. So we have this set. If we take lambda, omega equal to something small which is close to 0, then obviously the output must be -1, because that is the smallest one. If omega equal to 1, that will give us 7, because that is the largest one. Now, if omega equal to half, then because we know that we have here 7 integers, then should be the value of P here should be 4. So the output for this
computation must be the fourth smallest element on this multiset, which is 2. That is a further modification by Ibrahim thesis. Now we have this multiplication with the same matrix, but obviously different output because we take the second smallest element. Now we already know the basics, so simply we have multiplication of matrix, but we modify the output. And this is how we compute the operation. So this one can be we have multiset. Oh, sorry, wait. It should be this one. Okay. So we have take the maximum of for each P, where capital P is the set of all K subset of S. So we take the maximum first, and then we take the minimum, and then the other way around. We have P, but P here is the subset of set of S with n minus K element, and then we take the maximum. Okay, now for the problem formulations, classic, we have matrix A and we have vector B on the right hand side. We want to know what is X such that AX equal to B, classic in linear algebra. Now we have the modification in the operation. We have maximum and minimum, but we take the omega here as the threshold. Now, this is just some definition. We call the problem as the normalized when the right-hand side factor is zeros, which is really basic in Max Plus community, where the easiest way to solve this problem is when we change the right-hand side factor to be zeros. And there is a nice relation. This one has the solution X if only S is also the solution of this one, meaning we modify the matrix A to be A star, for example, by simply subtract every row of I with minus P, with Pi at all. Okay. And the first result, which is quite straightforward, if we have the normalized linear equation where we have two rows, let's say AI, the I row and the I column, if one of them is larger than the other, then the problem is obviously not solvable for any omega. Why? Because we have a relation like this. Sorry for audience in Zoom.
This one is
So because normally classic when we have X less than Y, then obviously when we multiply like this, should be. But because our right-hand side could be zeros, then when the I row is greater than 0, then cannot be both of them to be zeros. That's why the problem is not solvable.
the people no, they don't.
And this is just some notations. We divide the set of M, which is simply the set of integer from 1 until small m, and then we have the set of solutions. So I denote A with omega, and then this is the solution, the active elements. So because we know that the right hand side is 0, then this one the index, the element of A at row I and column GI is called active elements. And when we collect all active elements to be a tuple like this, then we call it as the solution index. And then this one is the set of all possible solution indexes. Now, for those of you who work on Max Plus or Min Plus, the problem is quite easy for Max Plus and Min Plus setup, which is when omega equal to 1 or almost close to 0. This is the result. And the solvability can be determined from a principle, which is candidate. So we have, unlike in the classical linear equation in algebra, we can do Gauss elimination and so on, but here we cannot do that at all. The idea is when we consider every columns, and then for max plus we take the largest elements, and then we put the minus, and that is the solution. Sorry, the candidate of the solution. If it is not the solution, then there is no solution at all. If it is a solution, then we may find other solution which is smaller. But if the problem is in min plus, we can do the same, but instead of maximum, we do the minimum. And this is the set of mi, which is we take the corresponding index, which is the largest or the smallest for each column of A. And one of the work by Bitkovic, which is one of the prolific researcher in MaxMin community, he had proved this proposition. This one solvable if only if the X bar, which is the candidate, is the solution, and the third condition also holds, meaning that when we collect every active element in its columns, it will become M, which is the set of set from 1 until M, small m. And this is the condition for uniqueness solution. Okay, now this is the last part of problem formulation. We define the problem to be column distinct if its column of A has distinct elements, otherwise we call it column indistinct. Now, our approach is, instead of directly trying to find the solution, we try to find the solution index because they are related to each other. Now, the first result we have is if the metric is column distinct, then the solution index must be a permutation of beta n. So the idea is like this. So because we know that one of them, when we multiply the first row and with this factor x, the result must be 0. That's why for each row here, sorry, columns here must be equal to xi or xj. That's why the minus one. So when we collect the every index here, ji and the gn, they cannot be the same. Why? Because this column has distinct elements. That is the reasoning why the solution index must be a permutation. Now the second result, the next result, if the metric is column distinct, then we have one-to-one correspondence between the solution set and the solution index, meaning that for each indexes we have exactly one solution and the other way around. So our idea is, instead of finding this set, we want to find this set. The next result, when the metric is column distinct, and we have a new metric which is P, which is generated by modifying a single element, let's say A, K, L. If the ordering of the element at the same row, sorry, the same column, which is the L column, is the same, then the set of solution index for both metrics with the same omega of atoms must be exactly the same. Unfortunately, the proof is quite long, so I don't put it in the slide. And this is the one of the most important discovery. We define another metric which is A bar is like this. So from metric A, remember that the column is distinct for its columns. The AJI equal to K if this condition holds. So in summary, if AJI equal to K,
meaning that these elements AJI is the k smallest element in the corresponding column, which is the I columns. I will give some example about this one. Okay, this one. So we have this matrix A. Sorry, I forgot to mention that for the next slide, we always consider the problem is normalized, meaning that the right-hand side is already zeros. Now the A bar metric is like this. So considering the first columns, we have 4, 5, 8. 4 is the smallest one. That's why we have 1 at the same location, and then 5 is the second one. Then we put 2, and then 8 is the largest. We put 3, and the same for the other columns. So because the columns is distinct, then for metric with dimension of n, in each column we have element from 1 until x with maybe different order. And the next result, we prove that from A to A bar, the set of solution index must be the same. And finally, this is the most important discovery. We prove that this permutation is part of the solution index for A bar if the total elements with the corresponding location must be equal to this one. Okay, this one. Remember that when this matrix C here is simply where this one Cij equal to A bar Aj plus Xj, considering that when you multiply the first row and then this factor X, then you put the additions in the first row. Now, because we have P here, sorry, P equal to this one, then we want to zero here as the output to be the P smallest element. That's why for each row of so for each row of C, we have exactly P minus negative elements, because we want to have something like this. We have, sorry for the audience in Zoom. So we have set with something with an element, and we have 0 here. It should be the P smallest element. That's why we have something negative. It is exactly P minus 1, and the other here should be N minus P, which is positive. Now, when we remember that in each column of A, they are distinct, and the element is 1, 2, until N. So when we take so exactly there are exactly negative element with this value. Now, in total, because the tuple here is a permutation, we take the total here. So n times p minus 1 should be equal to this one. And by simple modification, we can prove this one. Now let's go back to the example. So that is the A bar matrix. Now for the omega equal to 1/3, which is meaningless cases. Now because remember that the total must be equal to omega n, C times n. That's why for omega equal to 1/3, the total must be equal to 3. Meaning that find permutations, and then when you take and when you compute the sum, it should be equal to 3. So the only possible permutation is when you pick 1 here at the first row and the first column, and then you take another one, which is the second row and second column, and then of course the third row and the columns. The total is exactly 3, and then to find the solutions, put negative for all of them. Now, remember that this is the factor X bar is still the candidate, so we need to check simply to the multiplication, and for this example actually satisfied. That's why
this one is the solution for A bar. Now we go back to the metric A. How to do that? Simply do the same, because the solution index is 1, 2, 3 here. So the solution is -4, -2, -1. For omega equal to 1, which is max plus cases, the same, similar. Instead of because now the total must be 9, because omega is 1 times 3 and then times 3 again, it is 9. Now the only possible is this one, 3, 3, 3. So the solution index is 2, which is from the first row is 2, the second row is 3, and the third row is 1. And then for A bar, the candidate solution is X bar. And we check it is indeed a solution. Now for the original system, which is metric A, we can do the same, which is this one. This one, this one, this one. So from the first element should be -8, -7, and -5. So in max plus or min plus setup, or we don't really need this one. We take the maximum from each row, from each column. So the first column is 8, the second one is 7, the third column is 5, and then we put negative. And this is the interesting discovery. Why? Because for omega equal to 2/3, we have 4 candidates of the solution index, because the total must be 6. So one of them should be this one, 1, 3, 2, which is 1 plus 3 plus 2. The total is 6. Now for the solution index 2, 1, 3, the corresponding is 3 plus 2 plus 1. Now we have 4 candidates. And then when we multiply with the metric A bar, they are indeed the solutions. And because of the proposition, the solution index also belong to the metric A. Now, stop in this part. So in classical linear equations, we always have either zeros, 1, or infinite. There is no way we can have something between 1 and infinite. But in this setup, we can have a linear equation which has non-unique but finite. Okay, now for the second part, which is column in these things, when there are some duplicates in its columns. First of all, it is possible that for a solution X, the set of solution index more than once, because of duplicates in several columns, and then the corresponding tuples is not a permutation. Now our approach is trying to imitate the method for the column listing. First, we search for a permutation which belong to the solution indexes, and then find the corresponding solutions, and then find the other solution to the relaxation, meaning we can either increase or decrease some element of the solution X. It could be both at the same time. The generation of metric A bar is slightly different. Why? Because the column of metric A now have several duplicates. I think this is easy to explain by example. Okay, this matrix. Now we have this matrix A, which is 4 by 4. There are some duplicates in the first and the second columns. Now, because in the first columns we have everything is 2, so in the corresponding metric A bar in the first column is everything is 1, because 2 is actually the first smallest element. Now move to the second columns, we have -1 twice. That's why we put 1 and 1 here for the corresponding positions. Now move to 5. 5 is not the second, because we have -1 twice. That's why 5 is to be the third smallest element. Then 6 is the fourth smallest element. And then for the third and the fourth, there are no duplicates, so we can write 1 until 4 with the corresponding order. Now, we define Ti as the frequency of the mode, which is the element with the most appearance in the I column of A bar. And this is the modification of proposition 8. In proposition 8, when the matrix is column distinct, we don't have we have exactly with equal sign, while in the column indistinct we have lower and upper bound. The upper bound is given by this one, so n minus d, where d is the total of frequency in each columns. Let's have an example again. Okay, for matrix A, 4 by 4, the omega is a half. That is the matrix A bar. Now, because of, okay, this is the frequency Ti, meaning the largest frequency of the first columns on matrix A, which is 4, because we have 4 of 1s. Now, on the second column, we have 1 as the mode elements, and the corresponding frequency is 2, and then for the rest is 1. Now, the total of frequency is 8. Now, by proposition 9, when we want to find the permutation as the solution index, it should be satisfy this constraint, which is between 4 and 8. Out of 24, we have 14 possible solution index. Again, they are still candidates, so we have to check the corresponding factor whether they are solutions. For 19, there are 3 of them that are not the solutions. And then it is also possible that 2 different solution index or permutation will give us the same factor. For example, this one, 1, 3, 4, 2, which is this one in the red color for matrix A. So we have 2, 1, so minus 1, 2, and 2. Then put the minus, we have that factor x. Now for the second permutation, it will give us the same because of we simply switch this one to this one. In total, there are 9 solutions. Now, the next step is when we already find the solution from the permutation, which is a solution index, we want to find the other solutions by simply modify the element of x. It could be increase or decrease. Now, we call the solution x as fully active if for each j, there exists at least 1 such that this condition holds, meaning that for, okay, maybe okay, this one. If we have a matrix C defined as like this, then the factor x is a fully active if there are at least 1 0 at each column of C. Now, instead, we say an index J is increasable if there is another solution, which is x hat, where the location, sorry, the elements at J are greater than, or similarly, we call decreasable if we can find other solution where we decrease the J elements, and the other is the same. Okay, this is the condition for an index whether they are increasable or decreasable. So the first one is, remember that when we have these linear equations with normalized, which is the right hand side factor is zeros, and when omega times where are you? Okay, this one p equal to omega times n ceilings, then 0 must be the p smallest element. Now, because we want to modify one element, so there are at least 2 0 elements, because after we have 2 zeros, we may change, or in this case, we increase. That's why the number of 0 decrease. Now, Now we have n minus p minus 1 positive element because from the zeros it should be to be positive. Remember that in each row it should be at most n minus p positive elements. So the idea is we take specific columns and then we found whether there are zeros. Obviously, this should be at least one, and then for its corresponding location in row, and then we check the corresponding rows, and then we check whether each row satisfies these conditions. And this is the other proportion where the index is decreasable. The first condition is the same because we want to reduce the number of zero elements, and zero must be always exist in its row. That's why at least 2 zero elements. And then for a fully active solution, the relaxed solution for X is like this. So we can either decrease some element in this one, so the delta J should be negative, or we can also increase by epsilon J. Obviously, the epsilon J must be non-negative. In some cases, the relaxation of X is not unique. I will give the examples. And the rel, which is with the capital R, is the set of all relaxed solutions. Okay, now let's have examples. Okay, so this is magic A, the omega, the solution which is fully active from the previous examples, and this is the corresponding C. Now we look at the first columns, which is in red. So we cannot increase nor decrease y when we increase this value of X, which is -1, to be something bigger, then this one to be positive, all of them. Now, because we want to ensure that in each row, when we modify the element of X, there is at least 1 zero element, and the zero element must be the second smallest element because we choose omega to be a half. Now, when we have this one to be positive, the first columns, then if we look at the last row, 0 is not the second smallest element again. That's why we cannot increase. Now, we also cannot decrease it. Why? Because we look at the second column, sorry, second row, we have 2 negative value. That's why 0 cannot be the second smallest element. Similarly, the second index, which is for this one cannot be increased nor decreased with the same reasons. Now, index 3, which is this one, for the -2, this one, is only increasable. Why? When we increase this one, the 0 to be something positive.
Maybe you should try to use the mouse instead of because the people also don't see what you're doing.
Okay.
Yeah, but it appears to be about the problem which he's talking about. Yeah, but
so I point the location of what I'm talking about.
I hope that they can see the mouse. Yeah.
Okay. So
Mouse they should be.
okay, the index 3 is increasable. Why we have 0 here. When we increase this value of -2 to be something that is bigger than -2, then this one to be something positive. And we look at this one, 0 is still the second smallest element because we only have 1 negative element in the second row. And for the other, it doesn't matter at all. Why? Because the other elements in the third column is already positive. So when we increase, it's still positive. Now, in each row, the first, the third, and the fourth, 0 is obviously still the second smallest elements. Now, why we cannot decrease this one when we decrease this one, this 0 will become something negative. And in the second row, we have 2 negative elements. That's why 0 cannot be the second smallest element. Index 4 is only decreasable. Why? Because when we increase this one, we will have this one positive. Now 0 here will be the first smallest element and not the second smallest element. And we can decrease it. Why? Because when we decrease this one, doesn't matter, it will be negative. But because we already have 0 here, 0 is the second smallest element. And the other location doesn't matter because here still negative. And when we have this one, even though when we decrease by something really big or negative, then but we still have 2 0 elements, and there is only 1 negative element, and 0 is the second smallest element for the fourth row. Now, after we found which index is decreasable or decreasable, we need to find what is the largest increment. That's how far or how large we can increase or decrease the corresponding element. So for the third one, this one, we can increase it unboundedly. We can take to be plus infinity. Why? When we change this third element to be something plus infinity, then all columns here, the third column will be plus infinity, and it is easy to check that 0 is still the second smallest element. Now for the last index, index 4 is decreasable, and the largest increment is minus infinity. Why? This one is still already negative, when we decrease it's still negative. This doesn't matter now because here we have 2 zeros. Even though if we decrease it by minus infinity, then for the last row, 0 is still the second smallest element. And this is the relaxed solution of these solutions. So we can take any factor within this interval. So now the solution, we represent it as the factor of interval. So we can choose any element for its columns, its row in the corresponding intervals. Now we have another examples with different solutions. Now the only index that increases is 4, and the largest increment is plus infinity, because when we change this last column to be infinity, plus infinity, then for each row we still have 0 as the second smallest element. Now for the decreasable index, we have 2, 3, and 4. So we have at most 4 possibilities. So first one is, how about when we only decrease the second element, which is y2, which is this number 1, and now the largest decrement is minus 6. Why? When we decrease this one, this 0 must be negative. Now we have to careful with this one. We can, because this row already have negative. So the only possible or at the maximum modification for this one is to be 0. So when we decrease it more than or smaller than minus 6, then this 6 will be negative, and we cannot have 0 as the second smallest element. That's why the largest decrement is minus 6. And for the for the third row, the third column, we can do unboundedly, we can take the minus infinity. Only y4, the same reasons, we cannot, because in this row we have already minus 1, and at most this element can be modified until 0, because we want to ensure that 0 is the second smallest element. Now, when we modify y2 and y3 at the same time, which is these 2 elements, 1 and 3, the same reason we have the largest decrement for the second element -6. Why? Because we already have -1 here. Now, when we modify this one to be -6, when we decrease this column by -6, we already have this one in negative, and this one is negative. That's why we have to choose this either this one and this one. Then both of them cannot be negative. That's why the largest decrement is -3. When we want to modify y2 and y4 at the same time, it's not possible. Why? Because on the first row, we have 3 zeros, and if we decrease these two elements simultaneously, then we will have two negative elements. And in that case, 0 is not the second smallest element. Why? When we modify y3 and y4, that is the largest increment. For the third element is -4, the fourth element is -3. And lastly, obviously, we cannot decrease y2, y3, and y4 at the same time. And this is the possible relaxed solution with respect to this factor y. Okay, for the last part, I will mention some future work. Well, actually, our project here with Ibrahim and Syifa'ul is not finished yet. We want to consider when the metric is rectangles, meaning the number of rows and columns are the same. And for the next direction will be when we have a matrix A is not finite. So in the discussion, we always consider that the matrix is finite, meaning that all elements are finite. There is no minus infinity, there is no plus infinity. Now, for the next direction, we are interested to solve the eigenproblems. Why? Again, in max plus and min plus community, it's already done. It's quite easy. And for those of you who are not familiar, the method is completely different. We cannot find the determinants, and any method in linear algebra, the classical algebra, can be applied almost all. Now, okay, I give the example here. So for omega equal to 1/3, which is a min plus cases, then the eigenvalue is 1. Why? Because 1 here is the smallest element, sorry, the average weight of the critical circuits, and the corresponding eigenvector is this one. Now for omega equal to 1, which is max plus cases, and the eigenvalue is 6, which is the average weight of the critical circuit in max plus theta, which is this one, 7 plus 5 plus 6, the total is 8, and the average is 8. The total is 18, and the average is 18 by 3, which is 6. Now, for this one, for omega equal to 2/3, we are not sure yet. Well, the way I compute or find this eigenvalue and eigenvector is using a computer, and we don't know how to solve it analytically. And this one actually corresponds to this circuit, this one, the self loop at the node 1, and then there is another cycle, which is 2 and 6, and the total is 8, and then the average is 4, and then there is another cycle, 3 and 5, and the total is also 8, and the average is 4. And Sergey and me just have a lot of thinking about this one recently, about 15 minutes ago, and we realized that some of the result for max plus and min plus is not directly applicable for this MaxMin-Omega system. And the last one is the transition bounds. In max plus or min plus, this problem is already solved. We can always find the transition bound. So for those of you who are not familiar, transition bound represent the predictive behavior. So in max plus setup or min plus setup, when we have equation xk equal to a times xk minus 1, think of as a integral system, and when we do repeatedly, the sequence of factor is eventually fixed. Now, for the MaxMin-Omega, the metric multiplication itself is not associative. So, in fact, it is also not possible to define what is actually the power of a metric in MaxMin-Omega. It is still an open problem. We are not sure how to solve it, but of course, we are trying to break it. If we successful, it will generalize the concept that we have in max plus and min plus. Okay, that's all my presentation. Thank you for your attention.
Okay, thank you, Syifa'ul.
Thank you.
Any questions for Syifa'ul?
Yeah, I have already wanted to ask something about the associativity, but it's on the last slide.
Yeah, because the idea is okay. So I cannot write on the slide. So we look at there is a nice distribution rule. We have a times x plus y equal to a x times x y. Now, if we have this stacked up in max plus, we have o plus, then we have x o plus y. We have the same a times x plus a y. Now, why we cannot apply for the MaxMin-Omega? Because, well, actually, think of like this. Max2 of this one, sorry, the largest when we have this one and we have x, y, z. But this one is actually either like this minimum of max of x and y, max of x, y, z, and max of y and z. So actually, there will be three operations actually if we combine this one into max and inverse. That's why the associative or the distributive rule that is not apply at all. We are not sure yet how to define it.
No, well, concerning these transients, maybe we cannot do anything about powers. Powers can be driven to be defined. But you